So, welcome back to this class on hardware security. So, we shall be continuing our discussions on power attacks, and in particular today we shall be discussing about a topic which is called as mutual information analysis. So, we shall be trying to see how mutual information analysis can be developed. So, we will basically start with the preliminaries behind mutual information, or MI as it is abbreviated. We shall try to define mutual information and also conditional entropy, which are fundamental to the understanding of this technique. We shall formalize this with respect to side channel analysis and side channel leakage. Then we shall define what is the MI based distinguisher, and then I will be discussing about couple of toy examples and real life examples to illustrate how it works in practice. So, to start with, mutual information analysis, or MIA as it is abbreviated, is a general or generic side channel analysis distinguisher. So, like we have seen CPA and difference of mean, which were essentially like side channel distinguishers, which are built around the Pearson's correlation coefficient. So, here we try to apply the idea or theory of information theory and try to develop a statistical tool for doing power attacks. So, the objective is to perform side channel attacks with minimum assumptions and knowledge of the target device. So, for example, like when we were applying the CPA or difference of mean, then as I said that one of the reasons why the attack works well is because we basically make a tacit assumption that the leakage is underlying leakage is linear. Okay. So, likewise, right, I mean, and it is more like the correlation coefficient is more appropriate when the leakage is linear. Okay. But in this case, what the objective is basically, since it is more fundamental in its way the MI tool is developed, we basically can work with minimum assumptions and knowledge about the target device. So, MIA is also like the DPA and the DOM techniques, right, or the CPA technique is basically a non-profile attack. That means, it does not have any profiling phase, as we have seen in the context of template attacks. Okay. And its main advantage is that it can detect any kind of data dependency in the physical measurements. Okay. So, that is not necessarily linear, as we have seen in the context of DOM or CPA, and it relies on very strong fundamentals on information theory. Okay. So, it is important to make a quick recapitulation about how or what are the tools that we have in information theory. So, for example, let x be a random variable which is defined on a discrete space denoted as say psi, and x is an element from this space. Then we can define the Shannon entropy of a random variable on a discrete space essentially in this way. So, it basically captures the amount of uncertainty which is essentially basically it is a measure of uncertainty during an experiment, uncertainty in this random variable. Okay. So, as I know that if I have got an n bit of data, for example, then there are n bits of uncertainty or n bits of unknown that so that therefore, the entropy, right, in the, if I say to you that the random variable can take any possible n bit value, that means there are 2 to the power of n possible values, then the entropy of that variable is n. Okay. So, it is n bits in general. So, here we basically try to give a general formulation of how the entropy can be calculated. So, essentially it is probability of x equal to x, that means the probability that the random variable x takes the value of small x multiplied with the logarithm with respect to base 2 of the probability of x equal to x. And note that since it is a logarithm, right, and therefore, the value being lesser than 1, the probability being less than 1, the logarithm is negative. So, we kind of cancel that by a negative sign, and that is essentially the formula of how to calculate h x. So, likewise, we can define the joint entropy. I mean, essentially when we have got a pair of random variables like x and y, and therefore, this expresses the uncertainty one has about the combination of these variables. Okay. So, for example, it may happen that there are 2 jointly distributed random variables and some of them never occurs actually. Okay. So, therefore, that reduces the entropy of their joint, or rather it reduces the joint entropy. Okay. So, what we basically say, or the way to measure h x y is a natural extension of this formula, is that you replace these probabilities by their joint probability. So, you have got the same way we can formulate. Now, you have got probability of x equal to small x comma y equal to small y, that is the joint probability distribution. Likewise, in the log also we have got probability of x equal to small x, y equal to small y, but now the sigma is taken over both x and y. So, there is basically a double sigma written as single sigma. Okay. So, this is essentially how we can calculate the joint entropy of a pair of random variables. So, now we would like to define a very important definition of what is called as the conditional entropy. Okay. So, how can we measure conditional entropy? So, the easiest way probably like to formulate conditional entropy is probably to think of in this way, like let us assume that this y, okay, that is the condition y essentially takes a specific value say y. Okay. So, we write y equal to small y, and then we basically multiply the entropy of x given y equal to small y with the probability that y takes y. Okay. So, basically like this, from you can say that we are applying the kind of the law of total probability and we are measuring this entropy. Okay. And now, what we do is, so it is not specifically the total probability as such, but we are basically trying to find out the total entropy by like varying y over all possible values of y. Okay. So, now we would like to calculate h of x given y equal to small y. Okay. So, this h of x given small y can be easily calculated, therefore, now note that y equal to small y, right. So, therefore, this is basically I am kind of fixing the value of the condition. The moment I fix the condition, right, essentially I can write the corresponding description of this entropy in exactly the same way as we wrote the entropy in the previous case. So, now we will write probability of x equal to small x, because this x can take some value say small x, condition on y equal to small y multiplied with the log of probability of x equal to small x given y equal to small y. Now, note that these two things can be multiplied, and like from the definition of conditional probability, we can write that the product of probability of x equal to small x given y equal to small y multiplied with the probability of y equal to small y is nothing but the joint probability distribution of probability of x equal to small x and y equal to small y. Okay. And therefore, right, this is the corresponding. If you note again that the sigma is a double sigma, which is varying over both x and y. And very easy way, or I would say like a good way of remembering how the entropies are in relation to them is in the form of this Venn diagram. Okay. So, if you see this Venn diagram, right, this is your h x, okay, this is your h y, okay, and note that this region is h x given y. That means like that if I tell you that this is your h x space, okay, and I tell you that the amount of, so suppose I want to calculate h of x given y, that means since you know that like that y, suppose you have the information of y. So, the amount of remaining information which is there is given by this portion. Okay. That is why this stands for h of x given y. Likewise, this portion stands for h of y given x. Okay. And you can easily note that we can write like if I want that h of x comma y, then that is given by this total region. Okay. So, you can note that if I add h x and add h y, then it is more than h of x comma y. So, therefore, these kind of relationships becomes quite evident if you think of this Venn diagram. In particular, we are interested about this region, okay, and this region is called as the mutual information of x and y. So, therefore, you can easily see that h of x, right, essentially which is this total entropy is nothing but, so you can write that h of x is equal to h of x given y plus the mutual information of x and y. Okay. In other words, the mutual information of x comma y is equal to nothing but h of x minus h of x given y. Similarly, you can write with respect to y as well. Okay. So, therefore, this gives a kind of an easy way to kind of remember or understand how the relationships between these like these parameters are. Okay. So, therefore, mutual information is a general measure of the dependence between two random variables. It expresses the quantity of information one can obtain about x after observing say y. So, if I am measuring say I x colon y, it is the amount of information, right, which you are essentially measuring about say the random variable x by observing y. Since I x colon y is equal to y colon x, you can actually define in a commutative way also. So, you can say there is the amount of information about y which you are observing by say x. Okay. So, therefore, right, we can write I x colon y is equal to h of x minus h of x given y, that is what we have seen, and therefore, right, using the result that h of x colon x comma y is equal to h of y plus h of x given y. So, you can note that h of x like h of x comma y, you can write as if like it is I am adding h of y with h of x given y, right. So, therefore, you can also write that I x colon y is equal to h of x plus h of y minus h of x comma y. Okay. So, now I would like to measure this mutual information in terms of the various probabilities actually. Okay. So, now let us see how we can do that. So, I x colon y, you can also define it in this way. So, you can write this as nothing but this again is a sigma which is taken over both x and y, and you are basically multiplying like essentially you have got p of x equal to x, that is x takes small x, comma y equal to small y, the logarithm of the probability of x equal to small x comma y equal to y divided by the probability of x equal to small x and probability of y equal to small y. Okay. And this essentially is nothing but the sigma of probability of x equal to x, and you can split this probability of x equal to x, small x comma y equal to small y as probability of y equal to small y given x equal to x, and then multiply the probability of x equal to small x. Okay. And this part you can also write in this way by like elaborating this probability of x equal to small x colon comma y equal to small y in terms of this. That means like you can write this in this way, because if you want to kind of elaborate this part, then you can write this part as probability of y equal to small y given x equal to small x. Okay. And this is nothing but, and this you are basically multiplying with probability of x equal to small x. So, this essentially is equivalent, and therefore, this part will cancel with this part, and therefore, you will have probability of y equal to small y given x equal to small x divided by probability of y equal to small y. Okay. So, this is the way in which you can directly calculate the conditional probabilities, and from there you can estimate the value of this mutual information. Okay. You can calculate the value of mutual information. So, now with this background, let us see and try to see how we can apply MIA for side channel key recovery. Okay. So, here is one very fundamental paper published in Journal of Cryptology in 2011. So, this diagram is taken from this paper. So, you can observe that what we try to do here is there are certain random variables which have been defined here. One way to kind of conceptualize this is by considering that there is a device which is performing several cryptographic computations, and you denote that by say EKP. Okay. So, EKP stands for your encryption implemented, and it is processing on P, which is the plain text, and there is a fixed K key which is K, okay, which you want to determine by your attack. Now, the device under attack manipulates a target computation, like we have seen in context to the other DP attacks. There is a target computation. So, it could be the output of an S box, it could be the input of an S box, and so on and so forth. So, there is the device under attack manipulates a target computation and updates a sensitive variable. This sensitive variable is denoted as a V S comma P. So, in this case like this is V j comma P, but you can think of that as some V S comma P as well. Okay. So, V S comma P for a fixed input P. Okay. So, note that the actual leakage, okay, because the actual leakage, right. So, this is the like the actual computation is V S comma P. So, the V S comma P is the so there are two parts in the device. So, you see like when you are doing the thinking of the mutual information attack, then the attack essentially has got two parts, like as we have seen in other power attacks also. There is one part where you are basically having the device like the device means the actual device which is processing the actual secret key. Okay. The secret key is essentially denoted as say small k. This is the correct key, this is the actual key. Okay. And when you are computing this, then there is an intermediate target variable denoted as V s comma P. Okay. Now, this V s comma P, although this is the target variable, so this V s comma P denotes like essentially it is a specific target which you are choosing, but the leakage essentially is denoted as Y k comma P. This is an observable. So, this we called as the observable. Okay. So, this is the observable leakage, often we will denote it as O. Okay. So, note that although you are probably processing on a part of the key like S probably or part of the state, but when I am writing the leakage, then the leakage essentially is like is essentially K or denoted by K, where K is actually a secret key which includes the sub key S. Okay. So, therefore, it is including the sub key S. So, therefore, the total leakage will actually not happen only because of the part of the key, it will happen because of the part of the key along with the remaining parts of the key also. Okay. So, that total key is denoted as small k, out of which I am interested in a part of the key, because I am doing a divide and conquer based attack. On the other hand, when you are talking about the adversary, that means when you are doing the attack, basically you do not know what is the key. So, you try to guess the key, right. So, therefore, what you do in the attack is basically you try to guess the key and you try to do a prediction. Okay. So, you basically try to make a prediction and you derive something which is called as the leakage. Okay. So, you basically find out a leakage vector, and this is essentially denoted as L. Okay. Now, this leakage again depends upon the guess which you are doing. So, there is a guess of the key that you are doing, okay, and this guess essentially is kind of mapped by some function into a leakage. Okay. So, this guess let me denote it as say k star for example. So, therefore, the leakage will be parameterized by k star. So, therefore, I call that as L k star. Okay. And then my objective will be to define a distinguisher which will tell me whether the guess is correct or not. Okay. So, the guess right k star could be say j, and I want to find out whether this j matches with this s or not. So, s is the part of the key, and the attack is successful if j is equal to s. That means, you are basically guessing correctly a part of the key. Again, remember that the leakage right does not depend upon the part of the key, but the leakage depends upon the total key. Okay. So, therefore, right, let us see how we can do this, and we will try to kind of understand the working principle of the attack by essentially defining the following steps. Okay. So, therefore, here is the remaining part of the attack. So, in the guess phase, so therefore, the previous one was the when you are profiling and you are getting the observable O, and now you are trying to estimate the leakage S, I mean the leakage L. Okay. So, this is the guess phase, and in the guess phase the attacker guesses the part of the key say j, and the attacker computes the hypothetical sensitive state Vjp. So, this is the hypothetical sensitive state which you are targeting. Okay. So, therefore, I denote that as Vj comma p, and the attacker applies the leakage model. So, this is the leakage model that I will soon elaborate more. So, basically you make a leakage model, and again, so the leakage model could be something like a Hamming weight leakage model, and then the attacker applies the leakage model to estimate x j comma p. Okay. So, this is the x j comma p. So, therefore, y k comma p is the observable, something which you are observing, and x j comma p is what you are estimating based on your guess. Okay. And therefore, now for the successful attack you will basically apply a distinguisher d to compare these two different the different models x j comma p and the actual leakage. Note that this, why I have said are different models x j comma p, because x j comma p will depend upon the guess which you make. So, you will basically make j 1, j 2, j 3 and so on, and therefore, you will guess a part of the key, and you will try to see that whether x j comma p matches with your actual leakage. Okay. Something similar what we have done in the case of correlation attacks, where we are doing a correlation, but now you will be calculating this information or mutual information, and we will basically try to find out what is the best comparison results, and the idea is that the best comparison essentially will give you the correct sub key. Okay. So, therefore, right, here is an illustration of a univariate MIA. So, univariate MIA stands for the fact that you are basically guessing at a distinct time instant. Okay. So, consider that y equal to, so this is just an example. So, therefore, suppose y equal to HW S of P XOR S is denoted as, so this is nothing but S of P XOR S. So, therefore, P stands for the plain text, S for the part of the key, and S is the S box which you are targeting, and then I measure the Hamming weight of the corresponding computation, and then I add a Gaussian noise to that. Okay. So, therefore, right, I mean note that the target, right, when you are basically guessing, essentially you have basically you are making a key hypothesis. The key hypothesis is denoted as j, and you again measured HW of S of P XOR j, and you measure the Hamming weight of that, and you denote that as x for the corresponding hypothesis. Okay. So, now what we plot is basically the, so in this case this diagram shows the, so by the red line it shows the probability of y equal to small y. Okay. So, the probability of y equal to small y stands for the probability distribution of this y. Okay. And we also plot by these other graphs, we plot the joint probabilities of probability of y equal to small y and x equal to small x. Okay. So, note that we basically plot the joint probability densities for probability, that is probability of y equal to small y comma x equal to small x for different models of x equal to small x. So, why there are again different models? As I said, this will depend upon the corresponding guess that you do. Okay. So, the guess essentially in this case, right, it is a suppose you are making a guess of a portion. So, the guess, right, essentially can be say 0, 1, 2, 3 and 4. Okay. So, note that you are making this guess based upon the corresponding based on the corresponding Hamming weights. The idea is that you can reflect on this, that if your x takes different values like x equal to 0, 1, 2, 3, 4, you will observe here that this like what we note here by the corresponding y values are those cases, right. So, where the Hamming weight, we basically plot the we basically observe the corresponding values of y for the corresponding value of x. Note that in this case, right, when this is for the correct key guess. Okay. So, for the correct key guess, you note that if x equal to 0, then that means, right, I am corresponding to those cases where the Hamming weight is 0. Okay. And we know that y equal to 0 or y 0 essentially is the corresponding case where the Hamming weight is 0, and there is only one such candidate. Okay. Likewise, when you go to x equal to 1, there are 4 cases. Okay. Like you have got 1, 2, 4 and 8, all of them have got Hamming weight of 1. If you consider 2, there are more cases. Okay. Again, if you consider 3, there are 4 cases. Again, if you consider 4 Hamming weight, there is only one case, 1, 1, 1, 1. Okay. And that is y 15. So, now when you are making, therefore, right, I mean, you can observe that in this particular case, the marginal, if you observe, right, if you observe that the marginal probability is, or the marginal leakage probability is denoted as probability of y equal to small y, and that is plotted by this red line. Okay. So, you will observe that this marginal probability matches very nicely with your joint probability distributions. Okay. So, there is a nice overlap between them. Okay. Whereas, when you are guessing it wrongly, then it slightly differs. For example, the reason why it differs is because when you are guessing the key wrongly, then that means there is a kind of mismatch. Okay. And the mismatch you can observe again by observing this table. So, for example, again x equal to 0, 1, 2, 3, 4, these are all the Hamming weights of your like the guessed state, and these are the corresponding y values. For example, note that suppose note that for example, for 2, right, if you consider 2 now, like the where x equal to 2, in the previous case all these y values had Hamming weight of 2. Okay. But now this number will remain the same, that is the number of y values which will fall into the pocket will again remain the same, because you are just doing an XOR. So, therefore, like it is basically a permutation of this value. So, therefore, you will still have the same number of corresponding y values which will fall into the pocket of x. But the interesting thing is that out of here every y value does not have a Hamming weight of 2. Okay. For example, you can see that like y 3 will have a Hamming weight of of 2, y 9 has a Hamming weight of 2. Okay. And so y 3 has a Hamming weight of 2 and y 9 has a Hamming weight of 2. Okay. And there are no more. Okay. So, therefore, you see that the joint probability, if you observe a probability of y equal to 2 and x equal to 2 will not now nicely match with probability of y equal to 2. Okay. And this will fall much lesser. Okay. And therefore, right, I mean what will happen is, therefore, you will find that this does not match very nicely with your. So, therefore, in this way you can actually develop a distinguisher. This is essentially the basis why you can develop a distinguisher, because like depending upon whether your guess is correct or whether your guess is wrong, you see that the marginal probability essentially has got a nice correlation with the joint probability, and if your guess is correct, whereas if your guess is wrong, then that like that correlation is lost, or that I would say that that match is gone basically. So, let us not use the term correlation here, but let us say that the match is gone. Okay. So, therefore, right, this is the basic basis behind the attack, behind how we can develop our attack strategy, and therefore, what we do here is that so this is how we are basically like we can conceptualize the attack. So, we have got a target chip or target design IC, for example, and in that, right, basically it is processing some intermediate value, say W, and there are 2 channels here. Okay. In one channel, the device correspondingly process the secret key. The key is embedded, for example, here as K, and the leakage essentially is a side channel leakage. Okay. And there are 2 leakage directions you can see. So, there are 2 channels basically. Okay. In one channel we basically observe this EKX, okay, and the other one we basically use a measurement. So, the measurement gives me an O value. Okay. So, therefore, this EK, so therefore, the idea is that this leakage arrow, okay, so basically it processes on the intermediate value, say W, and then gives an estimate which is essentially denoted as LW. Okay. So, this LW essentially stands for your leakage. Okay. Whereas, when you are applying or you are taking your scopes and your probes, right, you get an actual power estimate, that is your observable power. Okay. That is denoted by O. So, that means the device which is denoted by IC carries out the operation EK, where K is the secret key which is modeled as a random variable, and the intermediate word which is being processed is suppose denoted by a random variable W on 0 1 n. Okay. Now, the side channel leakage, okay, which is say denoted as L or mathcal L, which will depend upon time and also on the word which is being processed by the IC. Okay. So, hence L contains information about the intermediate value W, and we model the output values of L as a discrete random variable L on the space of 0 to L, okay, from like 0, 1, 2, 3, 4 L and so on, where L is much lesser than or equal to 2 to the power of n. So, it can be like depending upon the corresponding state value, like suppose there is an intermediate value say W which you are estimating, depending upon the value of this W you try to estimate L, you try to estimate your leakage S L. Okay. And you also have an observed measurement which you are essentially measuring. So, therefore, right, you can formalize this these two channels in this way. So, the random variable L is observed by measuring a physical observable O. So, therefore, the idea is that there is a random variable L which is essentially the actual leakage, but you as an attacker are not able to observe that actual leakage, but you are getting a kind of modified version of that. So, you are basically getting something like O. Okay. So, this is denoted by this channel, where rather than observing L you are observing O as an attacker. But as an attacker also if you can guess W or you can make a guess on W, you can estimate the leakage L, okay, at some specific chosen time say tau. Okay. So, therefore, now the attacker what it does is that basically does several measurements by varying the plain text, and it observes different values of the observable. So, the observables are denoted as OXIT, which means you are it is nothing but the measurement traces which you are observing. Okay. So, you are basically getting different power traces and you are giving inputs which are denoted as Xi's, and you are observing the corresponding power values at different instances of time. So, you are basically observing the power consumption across time instances. Okay. So, you basically get lot of values of O. Okay. And now, what you basically try to do is you try to develop a goal for the mutual information adversary, and the idea is that the mutual information adversary, which basically what it does is it takes different input values say x1, x2 and so on till xq, okay, and then the corresponding measurements or observed side channels are like denoted in this multi-set, which is OX1, OX2 and so on till OXQ. So, this is your observed power traces, and then the side channel adversary experiment is defined as follows. You guess a part of the key. So, therefore, this is denoted as k for example, and now you basically also using this guess you basically calculate the values of the intermediate target register, which is a W, which I denoted as, remember W right here in this diagram. So, this W is estimated. So, the W is estimated based upon the input X and also the guess which you do on the key. Okay. So, therefore, now what I do is I mean guess means guess on the part of the key. Okay. So, now I guess this part of the key, and depending on all my inputs, right, I basically like observe the corresponding leakages, and I basically try to find out their like try to kind of apply a distinguisher on these guessed or estimated leakages with my observed output. Okay. And the idea is that it returns k star, and if my k star matches with k, then I say that my experiment was successful, and that gives me a measure of the advantage of my experiment. So, now what we try to do is we basically try to construct an information based distinguisher. Okay. So, to each possible key say k star k dash, which I like choose from 0 1 to m, I basically create these partitions of my input space. Okay. So, basically what it means is I now choose my input space and I divide my input space, okay, into certain partitions. Okay. So, these partitions are, remember that I have got an input x, okay, I guess a key. So, this k or key part, so suppose this is k dash, okay, and apply say the s box or some kind of function which is denoted as f. Okay. So, I get a value of f k applied on x or f k dash applied on x. Now, I applied a power model. So, this power model, this could be like the Hamming-Wade power model for example, gives me an estimate of its leakage. Okay. This leakage is suppose some value I. So, now what I do is I basically in one partition, suppose there is a partition for I basically put in all those x values which essentially falls into that partition. So, these are, if there are two x values which leads to the same I value, then they belong to the same partition. Okay.
So, this way I create this partition, and that is essentially denoted as HIK dash. Likewise, like I have got partitions for 0, for leakage 1, 2, 3 and so on, for all the possible leakage values. All these values together gives me this partitioning denoted as HK dash. Now, HK dash also induces a subdivision which is denoted as GK dash, okay, which is essentially nothing but, so if you consider like one of these leakages, say for example like let me write as like HIK dash. So, what is HIK dash? HIK dash would stand for all those like input values which leads to the leakage I. Okay. So, now what I do is in this, so therefore imagine that there is a bucket corresponding for Li or leakage equal to I basically observe all the observables which essentially goes into here. Okay. So, remember that I can have some observation O1, I can have some observation O2, likewise I can have several observations which can go over here, and they are not same. The observed power values are not same, but the estimated leakage from where you are basically like getting the, I mean basically right, I mean the leakage right is getting modified to O. So, although the leakage is remaining same, but this O can vary because of noise and several other parameters. So, all those things right which essentially goes into this bucket essentially are denoted as the various O values, okay, and this gives me this partitioning which is denoted as GK dash. Okay. So, GK dash therefore has got G0 K dash and likewise till GL K dash, indicating right that in one of these, like if I write GI K dash, then GI K dash would mean that like for all those input X values which are essentially has gone to this leakage or which has led to this leakage I. Okay. What are the corresponding values of the observables? So, all those observables which essentially are corresponding to those X values which has led to I are essentially observed in this partition, they are kept in this partition. Therefore, right, I am kind of finding out how many observables are there or what are the observables which are there. Okay. So, now with this definition, right, we can essentially go to calculate or define what is essentially the we can go and define the actual attack. So, therefore, now what the attacker does is therefore, the attacker guesses a key value k and computes fkx, okay, which is an intermediate result like S box of XOR k, and now I basically like, so this W is say some bits of fkx, okay, say it could be the Hamming weight also, but suppose it is some bits of fkx, say it is the 3 MSB bits. Okay. So, therefore, if I take the 3 MSB bits, like what I am trying to say is that if right when you are doing this right x XOR with k and you are applying the S box say denoted as f and you are targeting one of these outputs, suppose right my W is given by the first 3 bits over here, okay, and these 3 bits or the values of these 3 bits essentially will give me the corresponding leakage class. So, how many values can these 3 bits take? It can take 8 values, right. So, therefore, all of these 8 values are denoted by these leakage classes from L0. So, you can imagine that there are buckets like L0, L1, so on till L7, there are 8 buckets over there. So, now what I do is basically I know that suppose I like fix L0, I want to find out all the O values which have gone over here. So, therefore, it could be that O1 is like there is O1 is one value, O2 is the other observables, O3 is the other observables and so on. So, using that right I basically estimate this PO given Li. So, PO over given Li is nothing but the number of values which are there in Li, that means this stands for the cardinality of this Li set, and the numerator is nothing but all those xj values which has led to Li. I have found out the corresponding O values and I am basically observing that whether this Oxj is equal to O or not, okay, and that gives me a measurement of this probability distribution or probability O given Li. Okay. Likewise, I can calculate probability of O as nothing but total Q and like the total set of how many Oxj's is equal to O. Okay. So, this is the cardinality of this set. Okay. So, once you have developed these probability notions, okay, so what we can do is we can now measure the corresponding entropy. So, the corresponding entropy is therefore now given by this formalism. So, therefore, suppose I want to calculate, so we are all set to calculate HO of O given Li and also H of O, and therefore, we know that H of O given L is nothing but this probability estimation. So, there is probability of O equal to Oj, comma L equal to Li multiplied with log of probability of O equal to Oj given L equal to Li. Okay. So, therefore, right this leakage is estimated based on a guessed key and we call it as Lk, and then what we do is that in our mutual, for our mutual information estimation, we can either maximize this ILK colon O. So, we basically return that k for which this is maximized, or as you can observe that HO is constant, we can just minimize this parameter, okay, and that is denoted as this. So, we can basically minimize the conditional entropy HO given LK. So, now let us try to apply this on a toy example. So, this is a toy example of an S box, which is nothing but like this is a mapping, which is this is just a symbolic S box. So, what we do is that we basically model the power based on the Hamming weights. So, you can see here the Hamming weight 3 means I have written that the observable is 3. This the Hamming weight is 2, so the observable is 2, the Hamming weight is 2, the observable is 2, and so on. Okay. And now, what we do is we basically use it to do the attack. There is one further important point which should be mentioned here, is that the leakage function which I mentioned should not be bijective, because if the leakage function is bijective, suppose in this particular example I choose say all the 3 bits as my leakage value. Okay. That means, if I choose all the 3 bits of my output, right, of my output S box, then there are 8 possible classes. Okay. And you can, if you just think a while, right, you will understand that if it is so, then it is evident that because of this leakage function, okay, for all I, there will exist one j for which this conditional probability will be 1, okay, because the mapping will be bijective. So, there will be one case we always fall into that case, whereas for all other j's the probability will be 0, and if this happens, right, this HO given L will be 0 and it will not differ with k. Okay. So, therefore, it will not work. So, an easy way out therefore is that make the leakage non-bijective. Say for example, let us make it Hamming weight for example. You can also make it say the last 2 bits or the last 3 bits. Okay. So, in this case, if I make it like the last for example the Hamming weight, then this is the corresponding plot of the MI value with the key guesses, and you can see that in this case the correct key base is the first key base, and it is indeed correct. Okay. This is my correct key guess. Okay. So, this is the starting key, the next key. So, you can see that you can get peaks. Likewise, also note that you can get ghost peaks, like there are some keys, right, for which you can get wrong possible peaks as well. Okay. So, here is a further example on a present S box. So, present S box is being denoted here. So, in this case the correct key byte is at specific location, the number of trace is 2000. Again you see that now, right, you can get a corresponding peak. So, in this case the leakage is modeled again by the Hamming weight, and we indeed get a corresponding peak at the correct key guess value. Okay. So, in one case I have kind of simulated the power with only Hamming weight. In one case I have kind of plotted it with the Hamming weight, except that one bit is contributing more to the leakage. Okay. So, we have basically added an extra incentive for that bit. Okay. This is just to see whether our simulation works. So, here is a real life example where we basically target an AES 120 implemented on our Sakura G platform, and the power trace which is acquired by varying plain text at random. The experiment focuses again. So, this is my correct key, this is a 120 bit key, and I again focus only on the first key byte. So, we take 8000 power traces. Okay, we observe the corresponding observables O, and then do a similar mutual information analysis attack. So, therefore, what we do is we calculate, we are doing from the ciphertext now. So, therefore, we do S box inverse of x XOR k, where x is the ciphertext. Now, the leakage function is say the lower 4 bits of Fk, it could be the upper 4 bits of Fk as well. So, therefore, the moment you choose 4 bits, you have got 16 classes or 16 bins. So, you have got 16 bins. So, for every bin we again calculate h of a given Lk. So, note that h of Lk given Lk means that I am guessing the key, and depending upon that I am calculating this HO given Lk. Okay. And note that there are 256 like guessed possible values here, and therefore, we distribute the x values into the 16 bins along with their observed power leakages OX. We estimate this HO given L, and therefore, here is a plot of the mutual information. Again, you can observe that for the correct key guess, right, here you will get a peak here, and here is a zoomed version. So, you can see that the key is quite visible. So, again note that if you go back, right, and see the correct key was 4A, and indeed right at the 4A position you get a peak here. Okay. So, this shows very nicely that the mutual information attack works, okay, and it is working correctly. So, therefore, the mutual information is quite fundamental to understanding leakage. We discussed on the use of MI for side channel analysis. It works well when the leakage is not linear, for example, like DOM or CPA, which works probably slightly better when the leakage is linear, but it can even work in the MI can probably will work better when the leakage is not linear. And we discussed several case studies to see how MIA works and is an effective side channel analysis tool. So, here are a couple of interesting papers which you can also read. One version which was published in Chess in 2008
followed by another paper in Chase 2009, which tells us exactly or gives more descriptions on where to use mutual information and actually where probably not to use mutual information analysis. Okay. So, with this I would like to thanks to you, and we shall again join in the next class. Thank you.